In this video we're going to make sure that we can add and subtract on our CPU. The next video we will go on and we'll do the multiplication and division. Now after we've finished these two videos we'll move on and we'll actually change the assembly language program that we have here to make it a lot easier to program. So let's crack on with this now. So go ahead and open up the assembler debugger. Now if we want to do the add, we've seen this before but we might as well just go back over it. If we had two numbers we wanted to add, we'd have to have one of the numbers in one register. So let's say we're going to add the number 5 and we can put 5 in R0 and we're going to add that to another number, let's say a number 3, and we'll put that number into register R1. So we can assemble that and debug and we'll see that we've got 5 in one register, 3 in the other register. So we just need to use the add command, and this is going to add the source to a destination. So the source register's got R0, so we're adding 5 into the register R1. So it's 5 plus 3, so it'll leave a value of 8 in register R1, and we'll put the end command in here, assemble and debug, and we'll see we've got the value of 8. So the addition is quite straightforward. So let's now move on to the subtraction, and we're going to have to use 2's complement in order to perform this subtraction. In order to subtract one number from another, we're going to use something called 2's complement. Now we will be going over this in detail whenever we work through the floating point unit, but we might as well go over this simple idea at the moment in order for us to do a subtraction on our simple machine. So let's say we've got the number 5 here in decimal. We know that this is the binary for number 5 here, so that's a factor of 1, 2 and 4, so it's 4 plus 1 is a value of 5. And we can count up from 0 to 5 here, and we've got our normal binary counting here. Now what we could do is we could say that we could call the first bit here, which is the most significant bit, we could call it a sign bit. So if it's a value of 0, we can say that the number is going to be positive. So all of these numbers are positive numbers. If this value here of the most significant bit is a value of 1, then we could say that the number is going to be a minus number. So it means now that the most significant bit now stands for a sign. So we could see here that we could have the value of minus 5, and this is the 101, which is 5, and the value of 1 here tells us that it's actually a minus. So we could do that with the rest of these here. Now the only strange thing is we would end up with a value of 0, and this would be the minus, so we'd have a value of minus 0. But all of the rest of these will have a value of minus 1, minus 2, minus 3, minus 4, minus 5. So let's see if this is actually going to work. Let's say we want to do the calculation 5 minus 5. Now we know the answer to that should be 0. Well, that's the same as saying 5 plus the value of minus 5. So the value of 5 is given here, and the value of minus 5 from above is written here. But the thing is, whenever we add these together, we're going to get the 1 plus 1 is a 0. We're going to have the 0, and it's a carry 1, and we'll have a 0 plus 0, and we'll have the carry 1 here. Well, if 1 plus 1 is a 0 carry 1, and it'll be a value of 1, and we'll have the 1 at the end. So that's going to tell us that the actual value is going to be a value of, well, it's going to be minus, and it's going to be 1, 2, 4 and 8, so it's going to be minus 10. So that doesn't work. 5 plus minus 5 should equal 0. It doesn't equal minus 10. But let's persevere with this. So first of all we'll look at 1's complement. We have written here what we did in the last slide. We have our values for our minus 5, minus 4, minus 3, all the way up to a value of 5. So this is us changed the number so that the first most significant bit there becomes a sign bit. So now what we're going to do is we'll actually take the negative values here and we'll find the complement of them. So by the complement I mean we negate them. So we'll leave the first one, which is the sign bit, as is. So we've left the first one as they are normally. But what we'll do is we'll find the complement of these. So this first number here will actually come 1, 1, 1, 1, 0, 1, 0. And that's what we've got written here. And we'll now call that the minus 5. And take another one, for example here. The value of minus 2 will become 1, 1, 1, 1, 1, 1, 0, 1. So this is called 1's complement. So let's see if this is actually going to work. We've got 3 examples here. We can say that the 5 plus minus 5 should equal 0. So this is going to give us this value here. Now whenever we add these up, we're actually going to get the value 1, 1, 1, 1, 1. Now I suggest you go and check this for yourself. But this value here is actually the value of minus 0. So we could say that the value 0, well, it doesn't quite equal a value of minus 0, but we're getting close. We could also look at, say, for example, 5 plus minus 2. So that should be equal to 5 minus 2, which is 3. So the 5 again is this, and you can see that the minus 2 is this one here. So you just need to pick out the minus 2 there. And whenever we add these together, we're going to get this value here. So this value here is actually a value of 2. So still we've not quite got it right. It should be a value of 3, but we've done it and we've got a value of 2. And when we try 5 plus minus 3, it should give us a value of 2. But whenever we work through with this 1's complement, we actually end up with a value of 1. And it should be 2. So we're getting closer, but in each of these, you'd think is we're actually 1 out. If we were to add the value of 1 onto this, we would get a value over 3, and if we had to add the value of 1 onto this, we get a value of 2. And in a strange way here, you can add the value of 1 onto this. Instead of having a value of minus 0, we would have a value of 0. So let's look at that in the next page. So now we're finally getting to the 2's complement. We've seen in the last page here, we had the 1's complement, so we looked at the adding a sign bit on, and then we inverted the values for the negative values. And we've seen that we were 1 out of. So what we can do is, in 2's complement, we take the inversion here, and we add a value of 1 to it. So that means that this value here actually becomes minus 6, and this one here is minus 5, minus 4, and so on, all the way up to a value of 5. So let's see if this is actually going to work. If we do 5 plus minus 5 equals 0, well this is our 5 here, and in the 2's complement our minus 5 is going to be given by this one here. So whenever we add these two together, well 1 plus 1 is 0 carry 1, 1 plus 1 is 0 carry 1, 1 plus 1 is 0 carry 1, and so on and so forth all the way along. Now you notice here that in each occasion here we're actually adding 2 together, saying 1 plus 1, and this is 0 carry 1, 1 plus 1, and this is why it's called 2's complement, because we're continually adding in 2's. So that's correct, it gives us the value of 0, and that's a value 0 here, which is our decimal of 0. Now we can check 5 plus minus 2, that should give us a value of 3, so that's our 5, that's our minus 2 here. Now whenever we add these two up together, again we're going to have 1 plus 0 is 1, 0 plus 1 is 1, we'll have 1 plus 1 is 0 carry 1, 0 carry 1, 0 carry 1, again it's the 2's complement all the way along. So you can see here we're actually end up with a value of 3. Now you can check this one out as well, 5 plus minus 3, and you'll see that will give us a value of 2. So it does work. So let's see how we're going to implement this in our software. So in order to implement this, let's understand what's happening first. If we have 8 bits here, and this is an 8-bit 2's complement number, then this is going to give us the number minus 128. So the 1 tells us the minus. Now the next one down here would be minus 127, and as we counted along it would go down minus 126, 125, so on and so forth. Now if we were to look at this number here as the normal binary number, then this would have a value of 1, and this would be 2, 4, 8, 16, 32, 64 and 128. So the total number we could make out of this would be a value of 255. But in terms of the 2's complement, what's actually happening here is that this is again position 1, 2, 4, 8, 16, 32, 64. But this value here, although we call it the sign value, which tells us whether it's a positive or a negative, the actual value of this is minus 128. So for example, in order to get this value here, we're going to have minus 128 plus 0. So that gives minus 128. To get minus 127, what we're going to have is minus 128 plus a value of 1, which would be minus 127. And 126 would give us minus 128 plus a value of 2, and so on and so forth. So it means that the range that we could make from these 2's complement, is a range of values from minus 128 to plus 127. So in order to do the subtraction, say 5 minus 5, we know that's the same as 5 plus minus 5. So we can write the minus 5. Well, in order to get the minus 5, we would normally write that 5 as 1, 2, 3, 4, 5, 1, 0, 1. So this would be a value of 5. To get minus 5, we're going to have to negate this. So that would become 1, 1, 1, 1, 1, 0, 1 and 0. So the negation is actually the not function. So we're going to have to perform a not function. But after we've performed that, we're going to have to add 1. So we're going to have a not and a plus 1. So this would become 1, 1, 1, 1, 1, 0, 1, 1. So this number here is actually the minus 5. So whenever we add this one to this one, we're going to get the value of, well, 1 plus 1 is 0 carry 1, 1 plus 1 is 0 carry the 1, and we'll have 1 plus 1 is 0 carry the 1, and so on and so forth all the way along. That would give us a value of 0. So the 2 functions we're going to have to perform are a function of inversion, which is the not, and a plus 1. So let's go ahead and we'll implement this just now. So let's work out 5 minus 3. We're going to have to put 5 and 3 into registers. So let's put 5 into register 0. And let's put 3 into register 1. We can assemble and debug. So we've got 5 sitting in register 0 and 3 sitting in register 1. But what we want to do is 5 minus 3. So we're going to have to find the 2's complement of this. So we've got to find the 2's complement of the value 3. So we know in order to do that, we're going to have to negate this and add 1. So in order to negate it, we can put down the not. So we want to not the value of R1, and we want to leave that value in that register R1. So we may assemble and debug. We see that the negation, the not of this, is actually the decimal of 252, and you can see that if you go online and say open up a decimal hex calculator. So you just go online and you can put in decimal to binary converter, and you can see that the value over 252 in binary is actually all zeros, and then all ones and the last twos are 0. And that's the negation of this here, so it's all ones and the last twos are 0. And then we're going to have to add a value of 1 onto it, but in order to add a value of 1, we're going to have 1 sitting in a register. So we can put data, and let's say we just put it into R2 and we have a value of 1. So we're going to have to add this value of 1 onto the value that's sitting in register R1 at the moment. So we can do add the value of R2 to the value of R1, and it leaves the sum actually in R1. So we'll go and debug that. We say debug, we're actually forming a trace of the program here. So now we've got the value of 253. So finally, in order to do the subtraction, what we're actually doing is adding on the negative. So we're going to be adding on the value it's in register R0, which is our 5, to the 2's complement value, and the 2's complement value is going to be sitting in register 1. And it will put the final value into that register 1. So if we'll put the end command in here as well, and we assemble and debug, and you'll see each of the steps, and at the end we should end up with 5 minus 3, which is equal to a value of 2 in R1. So it does work. So we know that the addition does work, and we've seen it working before in the CPU, so we don't need to bother looking at that. What we'll do is we'll look at the subtraction here, and we'll make sure that it does actually work in the CPU. So click on the export and find your folder. So my folder here is in this point here. So Control C and Control V. So that's us exported the file to MySim. So let's go ahead now and we'll open up the CPU and we'll load it in and see whether it does actually work. So now that we've opened up the CPU design here, again you can go up to the pull down menu. Now you can't see it here, but you've been through this plenty of times before. So we press on the reset simulation and you press the reset down here. So that's it all ready to go. So what we want to do is right click, edit contents, and we want to open our file, and our file's MySim, and you can see here that it's now loaded up the program. So what it's going to do is put a value of 5 in R0, going to put a value of 3 in R1, it's going to subtract them, and it's going to leave the value of 2 in R1. So let's go ahead and see that it actually does this. So you can again go up to the pull down menu and click simulate and tick enable. So it's going to count through here and load the program up. Once it gets to FF, that's it fully loaded, and it will very quickly run through the script here. So let's see it doing that now. That's 5 and 3, and the final value is going to be a value of 2, and that's it ended. So you can click on simulate and tick enable just to stop it. So you see it does actually work. Now if you want, you could also change the program so that it actually puts the answer saying R2, so you would have a 5, a 3 and a value of 2 there. That's all for this video. In the next video we'll look at multiplication and division, and after that we'll move on and we'll update the assembler in order to make it much easier to write assembly language code for our CPU. So thank you for listening. I'll get you in the next video. Goodbye.